wrap our head around this complex medical landscape, we're going to break it down into 5 key areas. We'll start with the tissue engineering paradigm, then look at stem cell sourcing criteria, move on to scaffolds, bioceramics, and hydrogels, explore anti-scarring cascades, and finally wrap up with clinical standards and safety.
All right, part 1, the tissue engineering paradigm.
So, what exactly is the tissue engineering paradigm? Well, the absolutely crucial thing to remember is that successful regeneration relies entirely on the interplay of 3 core components. Think of it like a 3-legged stool. We need cells to do the actual rebuilding, materials or scaffolds to physically support those cells, and molecules to provide all the necessary chemical signaling. When these 3 elements are working together in perfect concert, that's when we achieve true structural regeneration, instead of just ending up with a dense, fibrotic scar. Now, when we're sourcing those cells, we really have to evaluate their developmental potential. We call this the potency hierarchy. At the very top, you have the totipotent zygote. This has literally limitless potential. It forms the entire organism. A step down, we have pluripotent cells, like embryonic stem cells and induced pluripotent stem cells. These can build any cell type in the body proper. Then we get more restricted. Multipotent cells, like hemopoietic somatic stem cells, are locked into specific tissue lineages. And finally, at the bottom, we have nullipotent cells. Think of your mature keratinocytes. They are fully differentiated, highly specialized, and absolutely restricted. Moving right along to Section 2, stem cell sourcing criteria. A huge player in this field are mesenchymal stromal cells, or MSCs for short. And actually, pay really close attention to that terminology. The International Society for Cell and Gene Therapy specifically designates MSCs as stromal rather than stem cells. Why? Well, because their primary medical mechanism is actually paracrine and secretory signaling. Basically, they secrete factors that work directly with the host's immune cells, rather than undergoing direct differentiation themselves to replace the tissue. Because of this, the ISCT requires a super strict biological ID check for MSCs. It's not enough for them to just stick to plastic in a culture. They must express a highly specific positive surface marker profile, specifically CD105, CD73, and CD90. At the same time, they absolutely must lack immune and hematopoietic markers, things like CD45, CD34, and HLA-DR. And as a final test, they have to prove their capability by differentiating into bone, fat, and cartilage lineages in vitro. So how do researchers communicate clearly about these complex therapies globally? They use this step-by-step doses framework to standardize every single aspect of the cell's journey. It's a real game changer by precisely defining the donor, the origin tissue, the separation method, the exhibited characteristics, and the site of delivery. We can eliminate critical variables. This guarantees reproducibility across clinical trials all over the world. Now, this next part is just fascinating. We can now use OSKM transcription factors to actually create induced pluripotent stem cells, or iPSCs. By taking standard adult somatic cells and reprogramming them using OCT3/4, SOX2, KLF4, and c-MYC, we can offer a patient-specific autologous cell source. And the best part, this brilliantly bypasses the major ethical hurdles associated with human embryonic stem cells, which historically had to be harvested from a blastocyst. Okay, let's jump into Section 3, scaffolds, bioceramics, and hydrogels. When we look at the material side of things, synthetic scaffolds generally fall into 2 main structural categories. First, we have non-resorbable permanent materials. Think of PMMA used in bone cement or Dacron used for vascular grafts. Second, we have resorbable polymers that safely degrade over time in the body, like PCl, PLA, and PGA. To actually turn these polymers into functional homes for our cells, we use specialized processing methods. For example, supercritical CO2 foaming creates porous monoliths, while electrospinning uses an electric field to spin charged polymer threads. This creates fibrous matrices that perfectly match native extracellular matrix geometry. Now, some materials aren't just structural. They're reactive and actively drive healing. Take bioglass, for instance. It degrades in body fluids, releasing calcium, silicon, and phosphate ions. This actually deposits a native mineral layer that chemically bonds to host tissue and actively recruits osteogenic cells. We can even accelerate that bone formation by doping it with strontium or lithium. On the softer side of things, we have hydrogels. Because they are roughly 99% water by weight, they allow for rapid passive diffusion of nutrients. This creates the absolute perfect shielding environment for really delicate tissues, like encapsulating pancreatic islets with alginate. There is a catch, though. Standard hydrogels naturally tend to slump before they can fully cross-link. So to solve this, advanced 3D bioprinting uses sophisticated support beds to hold that precise structural geometry. The Fresh system is a great example. It embeds the hydrogels in a gelatin matrix that is then gently melted away at body temperature, 37 degrees Celsius. Another fantastic animal-free alternative is the SLAM system. This uses a shear thinning particulate hydrogel bed that you just clear away with a simple water wash.
Let's move on to Section 4, Anti-Scarring Cascades and Interventions.
To prevent scarring, we need to understand the fibrotic cascade, which follows a very precise chronological pathway. It all starts when trauma triggers pro-inflammatory factors, including TNF-alpha, IL-1, IL-6, PDGF, and VEGF. This initial inflammation leads directly to the activation of TGF-beta-1. That TGF-beta-1 then recruits contractile myofibroblasts right to the site. And finally, those myofibroblasts deposit a dense, highly disordered type 1 and type 3 collagen scar. That exact cascade is what we desperately need to intercept.
Because we deeply understand that specific pathway, we can step in with highly targeted molecular interventions. For skin wounds, we can use TGF-beta-3. This competitively blocks cell surface TGF-beta-1 and TGF-beta-2 receptors, effectively stopping wound overcontraction in its tracks. And in the eye, where a corneal infection could cause blinding fibrosis, we use Decorin. It's a native proteoglycan that acts as a potent TGF-beta-1 antagonist. When delivered via a fluid gel eye drop, it dramatically suppresses scar markers, preserving corneal transparency and literally saving the patient from fibrotic blindness.
Finally, Section 5, Clinical Standards and Safety Guardrails.
Let's take a look at cartilage repair to see how this translates clinically. The traditional microfracture technique, where we drill into subchondral bone to bring marrow-stromal cells to the defect, is pretty problematic. Why? Because it yields mechanically inferior fibrocartilage. In stark contrast, we have autologous chondrocyte implantation, or ACI. This is a rigorous two-step process where native joint chondrocytes are harvested, expanded under strict good manufacturing practice standards, and then re-injected under a patch. The result? Vastly superior structural Highland Lake regeneration. And you know, the clinical value of ACI is actually recognized at an economic level too. It's formally recommended by health regulatory bodies like NICE for knee defects, specifically when its cost metrics fall below the threshold of £20,000 per quality-adjusted life year, or QLAY gained. So clinical efficacy really must align with health economics. But listen, we must strictly navigate some profound safety risks in this field. The most pressing one is tumorigenesis. Pluripotent stem cells carry a dangerously high risk of forming teratomas. To mitigate this, we have to demand absolute 100% differentiation purity prior to clinical use. Or we can use direct transdifferentiation, reprogramming one somatic cell straight into another, bypassing that volatile pluripotent state entirely. Another massive risk is vector safety. To avoid accidental oncogene activation, the field is actively transitioning away from genome-integrating retroviruses towards non-integrating platforms. We're talking things like the Sendai virus, adenoviruses, plasmids, or synthetic RNA. So, I want to leave you with this final thought. The entire future of this fascinating field rests on our ability to harness immense cellular power, while at the exact same time maintaining unbreakable safety guardrails for the patient. So how will regenerative medicine flawlessly balance the limitless potential of pluripotent stem cells against the absolute necessity of preventing tumorigenesis? It's a huge challenge. Thanks for joining me for this explainer. I hope it brought some real clarity to the incredible science of tissue engineering.